My job this morning is to introduce the speakers. Our first short course lecturer today is Professor Bethany Ehlmann from Caltech's Department of Geological and Planetary Sciences. She also has a joint research appointment at JPL, and she is a participating scientist on the Mars Science Laboratory mission. In 2013, the National Geographic Society recognized her as one of 17 world-class emerging explorers. Most recently, the American Geophysical Union awarded her the 2015 McIlwain Medal, which is the most prestigious prize for early career geoscientists. It is our great pleasure and honor today to have Bethany teach us about Martian geology and the history of liquid water on Mars.
Okay, so thanks everyone for being here, and to Yuk and Pin and Chen for being our organizers. I think this methane on Mars topic is incredibly important. So I'm going to give a talk on history of water on Mars. I only have 30 minutes to talk about 4 decades of research. So this will be necessarily brief and may be review to some of you who are more familiar Martians. But for those who are not, let's all get on the same page with what we're talking about here in terms of where was the water, when was the water, and what else was going on geologically. So when I started to put this talk, I gave a brief bit of thought to why we are all here, our potential causes of methane detection. So is it the grand slam home run? Are they metabolic products of extant microbial life? Chemical products of an ongoing process involving water, such as serpentinization or another groundwater-driven hydrothermal reaction? Could they be related to volcanism? Clathrates, that is these ice water materials from an earlier epoch. Breakdown of exogenous organic matter, or I suspect we may, by the end of the workshop, somewhere end up in the other category. But the intent here is to orient you especially to these first 4 mechanisms by giving some geologic context for Mars. So just Mars, half the radius of Earth, takes twice as long to get around the sun. The axial tilt right now is about the same as that of Earth, so there are 4 seasons. Our solar day is about the same. The solar flux, though, is less than 40% that of Earth's, which leads us to have this average surface temperature of about 210 degrees Kelvin. Now, of course, that is only the average temperature. One thing that is striking about Mars, and may be relevant to our discussions about methane, is the fact that the average diurnal temperature swing is also much greater. This is just an example of some of the measurements that were taken by the Opportunity rover that shows that at the equator, the average diurnal temperature range is somewhere between about 180 and 285 Kelvin or so. So substantial changes here. And at the poles, it can get down to about 140 Kelvin or so. Now, back to the facts here. So at the moment, we have an incredibly thin atmosphere, less than 1% that of Earth, so that's 95% CO2. And the surface composition is primarily basaltic, although with hints of potentially more felsic rocks and certainly substantial variability in the broadly basaltic composition. So a theme that I want to have, because my personal opinion is that the methane is likely related to some dynamic modern process, is that modern Mars is actually fairly dynamic, and that this present dynamism that we see might in fact be a key to the past. So many of you are aware, some are probably not, that Mars's axial tilt is actually quite a bit more chaotic than Earth. So the excursions of Martian obliquity are actually rather extreme. And in fact, they occur on a periodicity on the order of hundreds of thousands of years. So you can see some recent results from the modeling of Lascar. So we explore at this time right now, where Mars's axial tilt is about the same as that of Earth's. But you can see that even less than 1 million years ago, the excursions up to 35 and 15, and as I'll talk about in a little bit, actually even much greater excursions have really dictated where it is that we find the volatiles on Mars. And so we see evidence for subsurface ice, ice-related gully formation, and then, as many of you are aware of, these recurring slope lineae that made the news that are likely liquid water. So we're going to talk about these modern processes. We're going to also talk about some of what's going on in the past. So the modern processes would be on the far right-hand side of the timeline. And then I'm going to talk through this process of orienting our mineralogic record with our geomorphologic record of the activity of water on Mars, with a number of key events. For example, our sun was once fainter before reaching its present luminosity about 3.7, 3.5 billion years ago. The Martian magnetic field probably shut off before most of our Martian recorded history. And Mars has repeatedly been impacted and had volcanism. So we're gonna step through a timeline. This is going to be the slide that's gonna orient the entire 25 minutes left of this talk. I usually start from the past and move forward because I study the past, and that way I make sure when I run out of time, it's with the modern stuff. But since the methane was detected in the modern era, I feel it necessary that perhaps we should start with the present and work our way backwards. So we'll see how this goes. So let's talk about modern liquid water. So if you have been watching the news at all in the last 6 weeks or so, you're probably familiar with recurring slope lineae, these darkening streaks that have made quite an appearance lately. So we know what the press says. What does the literature say? And what are the data from all of our instruments say? So the data indicate that these are most active when the temperature on the surface is about 265 Kelvin or greater. So these are active in the summer. What is most enigmatic about these recurring slope lineae, which may be due to liquid water, is the fact that the source of the liquid water is incredibly ill understood. These occur on ridges and rims for which there's no availability to supply water from surroundings to the point of initiation of these RSL. So that leads to the thought, are they buried ice? Are they from an earlier epoch? Are they some sort of modern phenomena of ice from current atmospheric exchange, or are they deliquescing salts? Because of their temperature of initiation, it is thought, and I think this is fairly solid, that liquid water is involved. So you heard in the news that perchlorate salts are possibly involved. There's another set of argumentation out there that says they're freshwater. But regardless, so I think there is liquid water, sometimes ephemerally, on modern Mars. And that's actually pretty incredibly exciting news. Another hint came much earlier, actually, that liquid water could play a role even in the present. And that was from the Gusev crater and the Spirit rover, which in the course of its dragging one of its limp wheels in the latter stages of the mission had a nice trenching experiment going on behind the rover every time as it roved. And you can see that on one occasion, some of the salts that we turned up evidence of salts and just in the upper centimeters of the surface. Now, these are not going to be stable against erosion over billions of years of geologic time. They must be a modern depositional phenomenon. So in this instance, they are a combination of magnesium sulfate and then some other salt, not identified, involving chloride. It could be a chloride salt. It could be a perchlorate salt. The Spirit rover did not have the instruments to make that distinction. But it's also noteworthy that many salts, many hydrated sulfates, hydrated perchlorates, can exchange with the modern atmosphere. That is, there is a certain amount of Mars regolith breathing, if you will, of exchange of the waters of hydration into and out of the salts as we go through these temperature fluctuations. So Curiosity has firmed up this story with the measurements from the REMS temperature sensor, where here you can see relative humidity and temperature plotted, and that for the lower temperatures you can see the increase in relative humidity. Indeed, Martin Torres et al. Pointed out that we're just hitting the bottom of the stability field at the surface on Mars today of perchlorates and hydrated perchlorate salts, in this case the 8H2O. So their modeling work shows that there is a small window where liquid is at least stable against sublimation, if not from evaporation into a very, very dry atmosphere, in the subsurface at depths of only a few centimeters or so. Okay, so I think this is incredibly exciting because it does say that there are these small amounts of chemical reactions mediated by liquid water, even at the present. So I think we need to consider that as we consider the methane. Okay. What if now we step back and we look instead at more tens of millions of years to maybe a billion years timescale? That is, we're in the long Amazonian period of Mars that goes back until about 3 billion years ago. Well, during this period, it's thought that the obliquity changes that I mentioned earlier dominate the evidence for cyclical climate change that's preserved in the geologic record in layered deposits and, as I'll talk about in a moment, gullies. So this is back on obliquity for a moment on a slide here I've borrowed from Phil Christensen in terms of the animation, but it shows schematically that as you get obliquity changes, you deposit and then sublime ice from different parts of the planet. So the volatiles are definitely cycling around, and this gives an opportunity perhaps to create some of the more exotic species of clathrates that have been proposed by some as a source of the methane, and I'm sure we'll talk about that a little bit more later, but this is just to illustrate. As we go back in Martian time, it becomes more and more probable, actually, that the climate has experienced one of these extreme obliquity regimes, changing where the volatiles are and which volatiles are stable. So a bit more concretely, just an example here with one of Phil Christensen's early works. So they have proposed that snow may be deposited or as either as direct precipitation or as a condensate out of the atmosphere in some of the alcoves of craters and persist to the present, and that there may be a relationship between snow and gullies. Now, this is not universally accepted. Others would invoke dry processes almost exclusively to create the gullies. My own sense is that it depends which gully you're looking at, and we need to develop better geomorphologic criteria for that. So these gullies and pasted on terrains are located on a wide array of latitudes. One example of a modern gully that I think is certainly due to small amounts of liquid water in the present is one that was discovered by Sam Schoen et al. Back in 2009 and then analyzed with some of the HiRISE data to show this beautiful depositional fan. It's at the mid-latitudes here in the southern hemisphere of Mars. And based on superposition relationships with craters, they were able to show an age of only 1 million years or so in terms of at least small amounts of liquid they propose, creating the type of flows that led to this depositional fan morphology. Okay, so that's the whirlwind tour through about modern Mars to about 3 billion years ago. Okay, what's next? Well, I started on the title slide with evidence for these spectacular outflow channels. I don't have time to talk about them today. I don't think they probably bear on the Mars methane story. We can talk about that more, but they occurred in the Hesperian, so in the period from about 3.5 to 3.3 billion years ago or so. Some have proposed that they're due to pressurized groundwater release. Others have proposed that they're due to catastrophic melting of ice and then release in massive floods. Okay, so another component of the geologic history, in addition to water, that bears perhaps on the methane story is volcanism. And in fact, we do see evidence for volcano-liquid water interactions from those of us who study mineralogy like myself. The most outstanding example of this is in the Syrtis Major lava flows. This is the cone here of Nili Patera. It's about a little over 5 kilometers across that we're looking at the latest stage of volcanic activity in the Nili Patera cone. And indeed, we see these small little knobs that you can see in elevation decrease from the top toward the bottom here by about 50 meters. And there are deposits of hydrated silica. That's the white stuff that you're looking at here, and Keck et al. Have the spectral details. So hydrated silica associated with these volcanic features. Now, it's debated what the analog is. Are they something like a Yellowstone system with waters pumping through quite vigorously, or are they more of a gas-driven type system, such as what we see at Kilauea? But regardless, these sort of water volcanic hydrothermal systems existed. And the dates on this are a little bit challenging, but they're certainly younger than the early Hesperian. So that would place them at a maximum of sort of 3.5 billion years old, and perhaps as young as just a couple billion. So it's worthwhile to say, though, that even where we don't see mineralogic evidence of aqueous water-rock reaction, that there is evidence for volcanism that is quite recent. So this is a compilation, and it's an excellent paper for those interested in Mars's, the timing of Mars's volcanic history by Stephanie Werner. So you can see here, and I just want us to focus on what's over on the right-hand side of the screen here, which is all the evidence for modern-day volcanism, less than 50 million years, one data point anyway, associated in and around the Tharsis Rise. So that means, for the purposes of our methane discussion, that Mars's volcanoes were emitting volcanic gases as recently as 50 million years ago or so. Now, it is debated exactly what the composition of Martian volcanic gases would be, but it is potentially a source. Importantly, I think we don't yet have a great sense of what the Martian heat flow is broadly, so at what temperature we might expect liquid water, if any is present in the deep subsurface, but fortunately we'll soon get a heat flow measurement from the InSight lander. Okay. After that aside on volcanism and mineralogy and gases, let's now switch to sort of the fun part. And I could give an entire hour-long talk on this, as could some of you in the audience. But we'll take the whirlwind tour through evidence for Martian lakes. So one of the spots is one that we're exploring right now with the Curiosity rover. This is just one of the more beautiful pictures that shows the sort of the rhythmic sediment deposition of layers of coarser and finer grained material preserved in Gale Crater. And you may have seen John Grotzinger's paper that just came out that describes the lacustrine environment there. From orbit, and the tally is now at something like 150 to 200 impact craters, we see evidence for open basin systems. That is a crater where there is both an inflow and an outflow. And some of these actually preserve spectacular deltaic environments, such as this one in the Jezero Basin, where there are clays and carbonates associated with this deltaic system. Now, what we see from orbit in terms of mineralogy is that the composition of these lake deposits spans the iron, magnesium, clay, carbonate, all the way to more acid sulfate environments that include jarosite and alunite in certain locations. So it's clear the Martian lakes did exist, but they varied widely in pH for reasons that we don't fully understand but are just starting to study now. Importantly, however, at least as near as we're able to date the valley networks and those systems, it does appear that most of the activity was associated with the early Hesperian, late Noachian boundary. So in this study by Caleb Fassett and Jim Head, you can see the scatter around about 3.5 billion years ago. That is the age for all of the valley systems you see here that are in yellow. Now, interestingly, there is some evidence for younger valley systems, and these are all associated with the Tharsis volcanic complex that I mentioned was that which was most recently active, right, up to 50 million years ago in some of the small calderas. So that's our history of valley networks on Mars in terms of surface waters. Something I think that has been hugely important over large swaths of Mars history is the fact that Martian groundwaters have existed. So in addition to overland flow contributing to lakes, we certainly have input from a groundwater system, and this was first recognized when, and sort of confirmed by the landings at Meridiani Planum that showed largely dune-like and sandstone-like facies, but with occasional evidence for sedimentary environments and depositional facies indicating playa lakes, but then repeated episodes of diagenesis affecting these rocks, leading to the textures that you see here. So sandstones, but whose grains have been remineralized to create this sort of mottled appearance. These open spaces that you see here, they're not fractures. They're places where there was a crystal that was originally precipitated, then by the next batch of fluid going through underground, dissolved. And then, of course, these hematite concretions growing also within that matrix. So repeated episodes of slightly different composition groundwaters diagenetically altering the sediments and contributing to the mineralogy we see today. Now, this wasn't isolated to Meridiani. We see this, and I don't have a context map, I apologize. This is completely on the other side of the planet and about 30 degrees further south than Meridiani. There's a whole sequence of basins that are filled with clays and sulfates, such as Columbus Crater, Cross Crater, and a few others, where Andrews Hanna predicted groundwater upwelling by a Mars surface hydrological system. And indeed, in many of these, and I'm just showing an example from Cross Crater from an American mineralogist publication we've submitted, of alunite, kaolinite, so these acid sulfate type minerals within the basin. Now, they're not all acid. If you went over to Columbus Crater instead, it would be a completely different mineralogic assemblage. So groundwater, clearly important in early Mars history, extending forward to the future. And what controls the mineralogy and the acidity highly varied across the planet. Let's see. So another example that we see, I'm not going to dwell on it, I don't think it's relevant to our methane story, but it's worth to be aware of, is these characteristic layered phyllosilicate deposits that we see at Marth Vallis, Nili Fossae, Vallis Marinaris, where there are thick sequences of both what appear to be sediments as well as altered basaltic crust with a tens of meters to just a few meters thick sequence of aluminum phyllosilicates on top. Now, these actually correspond in timing, as near as we can tell, to approximately the timing of the lake formation, and they may be an indicator of more enhanced near-surface alteration. So if we were to look at a series of stratigraphies on Mars, the light blue color are those aluminum phyllosilicates that I was just showing you. You can see they occur toward the top of the stratigraphy in every instance that we've found them, and beneath a capping rock that's Hesperian. So it says that these formed no later than the early Hesperian on Mars, and we don't see them, although it may be an artifact of preservation, we don't see them in the thick basement sequences exposed in Vallis Marinaris, Nili Fossae, the lower parts of Marth, which is interesting. So now let's take next in the remaining 8 minutes to the most ancient part of the stratigraphy, the sort of the thick rocks of the definitively Noachian basement here. So we'll talk about some of the deep phyllosilicates, which I think because of the influence of groundwater on Mars, even extending, we know from the rovers, into the Hesperian, I think that this sort of subsurface environment that created some of these phyllosilicates is perhaps one of the most persistent ones. And for our purposes here in this particular workshop, this is interesting because we know that numerous types of water rock reactions can generate methane, and especially serpentinization reactions, that is, those water rock reactions that take place when olivine and low calcium pyroxene contents of the rock are very high. So this is an example just showing some of the aqueous minerals that we see on Mars. Your eye should be drawn to a few things. One is that the younger terrains, like our volcanic centers, lack these aqueous minerals. That is thought to be a timing effect. The other should be that these light blue dots, the phyllosilicates, are relatively globally widespread over the Noachian and Hesperian terrains. The third thing that your eye should be drawn to, and I mentioned it earlier, is that the various salt minerals, the sulfate salts, chloride salts, carbonate salts, their distribution is actually rather patchy, and that relates probably to the pH and water chemistry controls that we don't fully understand. But I want to talk about these blue dots, that is, these phyllosilicates right now that are globally widespread. What are they? Well, so the phyllosilicates themselves, it's very interesting, are hydrated silicates to generalize a little bit to include phases like zeolites, for example. So the hydrated silicates tend to occur in Noachian terrains. Where they occur in Hesperian or Amazonian terrains, they're almost exclusively associated with impact craters. Interestingly, and here the hydrated mineral detections are in red, a density map of the valley networks that we were talking about earlier is in the color charts. You can see that the hydrated minerals are not associated with at least what the modern day surface of Mars has in terms of valley networks. So this is interesting. It implies that multiple processes are at work in terms of liquid water on the surface. Most of the clay mineral detections are instead associated with impact craters, like what you see here. In fact, with CRISM and imaging spectrometers like the Omega instrument on Mars Express, with CRISM and Omega we can peer into these impact craters and then study the morphology of how the phyllosilicates occur relative to others. So this is just one example of thousands, literally, of a 50-kilometer impact crater here this is just west of Nili Fossae, where you see that the iron magnesium phyllosilicates and aluminum phyllosilicates are located in the ejecta blanket of this crater primarily. So the phases that are found in this crater include chlorite, they include illite, and they also include prehnite, identified by this 1.47 micron absorption feature. Now, of these, they can form in a variety of conditions involving liquid water. Prehnite, though, is the fingerprint that provides some temperature pressure conditions. This is just one slice out of the PT activity of CO2 space. But it shows that actually prehnite is relatively restrictive in its formation because it trades off against phases. It's a calcium aluminum hydrated silicate. It trades off against for example, calcite, the carbonate, when the partial pressure of CO2 in the fluid gets too high, but it tends to favor temperatures of between about 200 and 400 degrees, thus pointing to hydrothermal activity at certain points in Mars. Now, another indicator of at least groundwater flow, if not hydrothermal activity, is in the terrains around Nili Fossae, where if we look at the deep subsurface, I'm going to just keep zooming in here. So we're going to zoom in to a place where there is a stratigraphy of iron magnesium smectites with olivine and carbonate rich units above it, and you can see these spectacular raised ridges which have been interpreted to be conduits of mineralization during fluid flow that, now that the terrain is being eroded, are more resistant, and so they stand up as high stands. So finally, another indicator of this warm, wet subsurface in that particular part of the liquid water story is the presence of serpentine. So the best type example of serpentine was discovered in Chloritis Fossae, which is actually some of the most ancient terrains on Mars, and it's in this confusingly fractured region just south and west of Valles Marineris, in what's quite ancient crust, and there are these tectonic fractures in Graben that are from the Tharsis expansion. So in Chloritis, our serpentine here occurs. It's not a tectonic melange in the same way that it's used in geology today, but it's certainly just a mess, right? There's no structure to where we see serpentine versus where we see the other minerals, yet spatially the patchiness is quite clear. So serpentine in and around these ancient crusts, and this has been studied further now by Christina Viviano Beck, who, following up on the initial detection, has looked at these Taumesia highlands and found serpentine in several locations associated with them. Now, in the grand context of iron magnesium phyllosilicates on Mars, serpentine is still relatively rare. So this map is now slightly out of date given Christina's work, but we can add a few more detections in the ridge terrain around here and another one there. But serpentine is actually pretty sparse in comparison to other iron magnesium phyllosilicates that we see. And that could be a function of two things. One could be, well, that serpentinization wasn't actually all that common. That's option number one. Option number two is that serpentinization was fairly common, but most of it took place at depths that are greater than about 5 kilometers. That is greater than what was excavated by most impact craters. So it could have occurred, but at depth. And then the third possibility is that there used to be a lot of serpentine, but it's been since weathered and altered by all this other water. And so what we see are other kinds of iron magnesium smectites like chlorites and smectites rather than the initial serpentine. Nevertheless, I'll point out one special region, which is some of the most olivine-rich bedrock on Mars that has at least 25% olivine content, maybe more, in the Nili Fossae region. This is just at the boundary where the Syrtis lavas come over this olivine-rich unit, and there you can see there's this unit that will zoom in the box here that has olivine, carbonate, and serpentine, and the terrain is spectacularly fractured here. And you can see on a sort of meter scale these polygonal fractures in the unit, which is consistent with what we would expect from serpentinization type reactions and the volumetric expansion that occurs, but not uniquely so. Okay, with 20 seconds left, so we've now marched through from modern Mars, history of some of the water environments, all the way back to the present. So I hope now when I switch to this slide that it all makes a bit more sense in terms of, right, we have our ephemeral activity on modern Mars, some of the most recent valley networks associated with the volcanic centers that may have been active even in the last 50 million years or so, stepping back with the outflow channels, and then the period of widespread valley networks and lakes on Mars. And this Hesperian to Noachian period was really the period when at least the mineralization at a scale and extent that's seen from orbit was present, including some of it being alteration in the subsurface. So I'll leave that up, I think, when I end, just some potential causes of methane detection, and you can ask me questions about the material before and how it relates to our potential methane. So thank you.